Recursive Language Models, or RLMs, are a task-agnostic inference strategy that lets language models handle extremely long contexts. Instead of making a single completion call, the model can examine its input, break it down, and recursively call itself on subinputs. RLMs replace the usual completion interface, turning a simple LLM completion prompt model into RLM completion prompt model, and treating the language model as a program that interacts with its own context. The design behind RLMs follows a code-act-style harness. Every language model has access to a code environment. Subcalls are expressed as functions in code, and the prompts and context become objects. By deferring execution to the model itself, the system remains very flexible and scales well, especially when trained properly. The authors prefer this approach over the JSON toolcalling standard, believing that a recursive language model structure is itself a language model, a probabilistic mapping from text to text that relies on recursive sub-LLM calls. This repository supplies both an extensible inference engine and a training environment to use RLMs with standard API-based and local LLMs. The initial ideas were announced in a blog post in late 2025 and expanded in an RZIV preprint. The project also includes a verifiers training environment that builds on Prime Intellect's Primeral framework, allowing you to train your own RLMs that can be plugged into the inference engine. The codebase supports several REPL environments. Non-isolated environments run directly on the host machine using Python's exec calls. They are suitable for low-risk local testing but must be used with caution in production. Fully isolated environments run on cloud-based sandboxes, such as Prime sandboxes, modal sandboxes, or Docker containers, to keep code execution completely separate from the host. Supported local settings include local, Python, Docker, modal, Prime, Daytona, and E2B. For IPython, the environment can run either in persys or in a separate IPy kernel subprocess, offering stricter timeout enforcement and namespace isolation. To install the library, you need Python 3.11 or newer. From PyPy you can run pip install RLMs. The default client uses a REPL environment that shares the host's virtual environment, allowing it to access the same dependencies while operating under limited global modules. For a quick example, you would create an RLM instance pointing at an OpenAI model and request a completion. From RLM import RLM. RLM equals RLM backend equals OpenAI. Backend quargs equals model name GPT-5 nano. Verbose equals true. Print drum completion print me the first 100 powers of 2, each on a new line response. For a manual setup, the repository uses of to manage dependencies. First install of, then initialize a virtual environment with Python 3.12 or another desired version, and finally install the package in editable mode. A makefile is provided for common tasks such as make install to set up dependencies, make check to run linters, formatters, and tests, and make quick start to run a sample query using your OpenAI API key. The project also offers a simple reinforcement learning training harness. It uses the same local REPL environment and can be extended with new environments by creating a verifiers environment that wraps your task. The harness plugs directly into Primeral, allowing you to launch training jobs with a TOML configuration. Detailed instructions are available in the training README, and an example long context question non-swearing environment appears in the training environment along directory. If you use RLMs in your research, please cite the paper. Zhang, Alex L., Kroska, Tim, Kadab, Omar. Recursive Language Models, RZIV, 2026, doi, 10.48550 RZIV, 2512.24601. RLMs have found use in a variety of demos and production ROI systems. While the original paper lists a number of notable examples, the repository's documentation encourages readers to explore these real-world applications. When debugging or analyzing a run, each completion can optionally store a full trajectory. By passing an RLM logger you can retrieve all iterations and subcalls. In-memory logging simply sets logger equals RLM logger, whereas saving to a directory produces JSONL files suitable for a visualizer. The visualizer is a lightweight Node.js application. To launch it, navigate to the visualizer directory and run npm rundev, which starts a local server at http://localhost:3001. This tool lets you inspect the generated code, see how the RLM interacted with the REPL, and trace every recursive call.